I'm going to show you how to find the cell potential of any electrochemical cell. So your first question might be, what is cell potential? Cell potential is essentially just measuring the potential between the two different half reactions in an electrochemical cell. So it's measured in volts. Basically, it's just a measure of how much work is needed to transfer an electron from one side to the other. So if it's an electrolytic cell, then that's work that you're putting into it to move the charge from one half reaction to the other side. And if it's a galvanic or voltaic cell, then that's how much work you're getting out for every charge that is moving. So the bigger that cell potential, the more work that you can get out of the system, the more positive it is, and the more negative it is, the more work that you need to put into the system in order to have that reaction progress. So I've written here on the screen an example. You might have a reaction where you have copper and chlorine interacting, and we would want to know what is the cell potential of this reaction. The first thing you want to do is split this up into its half reactions. So what's being reduced and what's being oxidized. Remember, if it's being reduced, that means that it is gaining an electron, or its charge is becoming more positive. So if you look here, copper by itself has a 0 charge. So copper is going from 0 to +2, meaning it's losing electrons, meaning it's being oxidized. So we can write the copper half reaction down here. It's going from copper to copper 2+. That means that what's being reduced is the chlorine, which is going from a charge of 0 because it's by itself to a charge of -1, so it's gaining electrons, meaning it's being reduced. So we can write the chlorine half reaction here. Now we need to balance these half reactions. Sometimes this is really complicated and you have to use that whole balancing by the half reaction by the acidic method. But in this case, it's pretty simple because all we're missing is electrons. So let's look at the chlorine first. Over here, we have a negative charge, but there's 2 of them. So we need to add 2 electrons onto the other side of the reaction. In the case of the copper, we have a +2 charge here, a 0 charge here. So we're, again, just missing some electrons, but this time we need to put them on the product side to make the total charge on the product side 0. Which is the same as the reactant side. Now our half reactions are balanced. And so the next thing we want to do is look at your reference sheet. So your reference sheet has a chart like this on it, and you want to find the reactions that you're looking at. So if we start with the chlorine reaction, we want to find that exact same reaction on here, and we see it here. We see it has a standard potential of 1.36 volts. So the electrode potential here under standard conditions is 1.36 volts. Now we can look for the copper one as well. But when we find copper, notice, just as a side note, there's like 3 reactions that have to do with copper, and that's because copper has more than one potential oxidation state, so you have to be very careful and look for the one that has the charges that you're looking for. This copper, right here, copper 2+, going to copper metal. Now notice this is the reverse reaction of what we have written here. Here we have copper being oxidized, but these on your reduction potential reference sheet are always going to be reduction, right? So if you have an oxidation, it's the same reaction, it's just backwards, right? This is at equilibrium. So what we do is we take its electrode potential and we write the opposite sign. So this one's electrode potential is -0.34 volts. So we reverse the sign because the reaction is being oxidized. So it's going to have the opposite potential as the reduction would be. Okay, and then to find the cell potential, so these are electrode potentials that we found on our chart. The cell potential is when you pair those two together. And all you have to do is add what you found on your chart, making sure you use the reverse sign for the oxidation. So in this case, the cell potential is 1.02 volts. Let's look at another example. So here I've written 2 half reactions. And let's ask a question. If this is a galvanic cell, which one is going to be oxidized, which one is going to be reduced, and what would be the cell potential? Now remember, a galvanic cell means what? A galvanic cell means that it's spontaneous, and if it's spontaneous, that means that your E cell, or your cell potential, is going to be positive. So we want to look at this and ask the question, how can I make this cell potential positive so that it'll be spontaneous, right? We have two half reactions, but both of them are being reduced. Now that's impossible. An oxidation-reduction reaction is where an electron is being lost by one species and gained by the other. So one will always be oxidized and one will always be reduced. The question here is which one is oxidized and which one is reduced. In order to find that, we go back to our handy-dandy reference sheet, and only this time we're looking for these other reactions. So we have the reduction of magnesium, that was one of them, and the reduction of aluminum. So these two values are what we're going to use. If we go over here, the reduction of magnesium is negative 2.38 volts, and the reduction of aluminum is negative 1.66 volts. They're both negative, and we can't have them both being reduced. One of them needs to be oxidized. We said this is going to be a galvanic cell. We wanted to know how this reaction would proceed spontaneously, which means our E cell, when we add these two together, it needs to be positive. So what we want to do is look at which one is more negative, and we're going to flip that reaction around so that in the end, our end result is something positive. So since magnesium is more negative, we're going to take this reaction, but we're going to write it in the opposite direction. So we're going to say the magnesium is oxidized while the aluminum is reduced. Okay, so then if you've switched the direction of the reaction, now we will switch the sign of this electrode potential. Okay, to find the cell potential, you just add these together. Now our cell potential is going to be, because this is a positive value, we know that this is a galvanic cell or a spontaneous reaction. And we can answer the question we asked at first. If you actually put this into like a beaker, you had your aluminum and your magnesium, ions floating around in there, what you would see happen is this solid, so you would start to see some aluminum plating onto some sort of surface, and any magnesium chunks you had would start to wither away and dissolve into the solution. So the key to finding the cell potential is looking at the electrode potentials, and you have to always make sure that one electrode is being oxidized while the other one is being reduced. If you're looking for a galvanic cell, the cell potential, or the sum of the two potentials, should be positive. If you're looking for an electrolytic cell, then the sum of the two would be negative. Or if you're given the direction that the reactions are proceeding, you can tell if it's spontaneous or not based on the sign of the cell potential.